10 Kelvin, not 10 degrees below the freezing point of water, not 10 degrees below the coldest recorded winter on Earth. 10 degrees above the coldest temperature that can exist anywhere, above the floor of all possible heat, above the point where molecular motion itself would cease entirely. 10 Kelvin is a cold so complete that it sits outside the range of anything the body has ever registered, outside the reach of any instinct or memory of cold. The surface of Pluto, far out at the edge of the solar system, where sunlight arrives as little more than a bright star among other stars, reaches temperatures of around 40 Kelvin. That is 4 times warmer than the interior of a dense molecular cloud core resting in the dark between the stars. This cold does not feel like cold. There is no wind carrying it. There is no surface for it to settle on, no sensation to announce it, no body to receive it. It is simply the condition of a place, a vast, still interior place, sealed from the light of every nearby star, insulated by its own density from the faint warmth that permeates the galaxy's general radiation field. Inside the deepest part of a molecular cloud, the temperature holds at 8, 9, 10 Kelvin and is held there for millions of years. Nothing in the solar system, in the warmth and light of a nearby sun, comes close. These clouds are not empty. They are among the most material-rich environments in the galaxy, though the material is so diffuse that a jar full of it would seem, by any earthly standard, to be a perfect vacuum. The gas inside a molecular cloud core is 1,000 times less dense than the best vacuum a laboratory can produce on Earth. And yet, across distances of tens and hundreds of light years, that thinness accumulates into something of extraordinary consequence. A giant molecular cloud, one of the great structures that drift through the spiral arms of the Milky Way, can contain a mass equivalent to 10 million suns. Some hold less, very few hold more, but all of them hold enough that their interiors have become, over time, something more than simple gas. They have become places where molecules form, where structure develops, where the cold organizes itself into shapes and gradients and densities that prefigure, very distantly, the birth of light. The most abundant molecule in these clouds is hydrogen, 2 atoms bound together into a single molecule, drifting through the cold interior, colliding rarely, moving slowly. Molecular hydrogen makes up something close to 70% of the cloud's total mass. Helium, unreactive, unchanged, since the early universe forged it, comprises most of the remainder, roughly 28%. What is left, all the other elements and molecules combined, amounts to a fraction of a few percent, and yet that fraction contains the entire chemical complexity of the cloud. The carbon, the oxygen, the nitrogen, the sulfur, the silicon, the iron, all of it representing the legacy of every star that lived and died in the galaxy before this cloud assembled itself from the swept-up remains. The temperature in those deepest cores, 8 to 10 Kelvin, places molecular clouds among the coldest, naturally occurring environments in the observable universe. There are colder places. Laboratory experiments on Earth have cooled small samples of matter to within a billionth of a degree of absolute zero. But in nature, in the wild physics of stars and planets and galaxies, the cold cores of molecular clouds sit at an extreme. They are colder than the cosmic microwave background radiation that fills all of space, that faint, uniform glow left over from the earliest hot moments of the universe, now cooled to about 7 Kelvin. No, the microwave background is colder still, but inside a molecular cloud, the dense gas and dust absorb that background radiation and re-emit it, maintaining the interior at temperatures slightly above it. The result is a cold that is ancient, quiet, and stable, a thermal equilibrium sustained over timescales longer than the history of the solar system. A giant molecular cloud spans somewhere between 50 and 300 light-years from edge to edge. 300 light-years. To begin to feel what that means, consider that the nearest star to the Sun lies just over 4 light-years away. A 300 light-year cloud would contain the Sun, its nearest neighbor, and roughly 75 of the next nearest stars, all contained within a single structure that is from the outside dark, diffuse, and very nearly invisible. The Milky Way holds several thousand such clouds scattered across its disk, concentrated in the spiral arms where the density of galactic material is highest, where the compression of passing spiral density waves pushes interstellar gas together into regions dense enough for molecules to survive. They are not uniformly filled. Nothing in nature fills space uniformly. A giant molecular cloud has a hierarchy of internal structure, a nested architecture of density and form that ranges from the diffuse outer envelope down to something far finer and more concentrated at its center. At the outermost edges, the gas is thin, barely molecular, exposed to the ambient radiation field of the galaxy that can dissociate molecules back into their constituent atoms. Moving inward, the gas thickens. The radiation cannot penetrate as far. Molecules survive in higher concentrations. The structure begins to develop a character. The outer envelope gives way to denser clumps, regions where the gas and dust have accumulated to higher concentrations, perhaps 100 times denser than the outer cloud. Those clumps contain finer structures still, elongated filaments of denser material threading through the interior like the grain of very old wood. And the filaments at their densest narrow into cores, compact, cold, nearly spherical regions of gas that have accumulated mass enough to begin, under the right conditions, to do something more than simply exist. The cores are the innermost rooms of the cloud. They are where the cold is deepest, the density highest, the silence most complete. This hierarchy, envelope to clump, to filament to core, is not accidental. It is the signature of the cloud's internal physics, the turbulence, the magnetic fields, the gravity and thermal pressure, all acting together across decades of scale to produce a structure that is in its way as organized as the branching of a river system or the architecture of a lung. Wide at the outside, narrowing inward, detail resolving from detail, the large giving way to the small. The same form appears at scale after scale, which is the character of systems shaped by the same forces acting repeatedly across many sizes. Interstellar dust is threaded through all of it. Not enough to see in any one place, the dust-to-gas ratio by mass is roughly 1 to 100, so for every gram of dust, there are 100 grams of gas. But across the immense distances of a molecular cloud, that 1% accumulates into something of significant optical consequence. The dust grains scatter and absorb light at sufficient column densities, the total amount of material along a line of sight. They block light completely. A single interstellar dust grain is a small thing. Most of them range from a few nanometers to roughly a micrometer in size. A micrometer is a millionth of a meter, roughly the width of a bacterium, far smaller than anything visible to the unaided eye. The smallest grains are smaller still, clusters of a few hundred atoms, barely distinguishable from large molecules. In composition, they are varied. Some are silicates, minerals similar in chemistry to the rocks of the Earth's mantle. Some are carbonaceous, built around chains and rings of carbon in forms resembling soot or graphite or more complex organic structures. Many carry a thin outer layer, a mantle of ice accumulated over millions of years in the cold interior of the cloud, built from water and carbon dioxide and other volatile molecules that have frozen onto the grain's surface at the temperatures that prevail deep inside. A single grain drifting through the interior of a molecular cloud has not been touched by significant light or warmth in an enormous span of time. It moves slowly, at the speeds characteristic of the cold gas that carries it, velocities measured in fractions of a kilometer per second, slower than the slowest human spacecraft. It collides with other gas molecules on timescales of months or years, accumulates its icy mantle, one molecular layer at a time, over millions of years, and drifts through a darkness that is, by any measure, complete. Light from the nearest stars cannot reach it. The faint warmth of the cosmic microwave background barely touches it. It exists in a thermal and optical isolation that has no counterpart anywhere in the solar system, at any depth, at any altitude, in any season. The way dust grains interact with light is not equal across all wavelengths. Shorter wavelengths, the blue end of visible light, the ultraviolets, scatter more efficiently than longer ones. A blue photon encountering a dust grain is far more likely to be deflected from its path than a red one. This is the same principle that makes the sky blue on Earth, where air molecules scatter blue light from the sun in all directions while red light passes through more directly. In a molecular cloud, the effect is more severe and the cause is slightly different. The grains are larger than air molecules, but the principle of wavelength-dependent scattering still applies. Stars seen through dusty regions of a molecular cloud appear redder than they actually are, their blue light scattered away before it can reach an observer, their red and infrared light passing through with less impediment. Astronomers call this reddening, and it is one of the primary signals through which the presence and depth of interstellar dust reveals itself in observations. The dust does more than redden. In sufficient quantity, it extinguishes. Where the column of dust along a line of sight becomes dense enough, the light from background stars does not merely diminish, it disappears entirely. The dimming is measured in magnitudes, the astronomical unit of brightness. One magnitude of extinction corresponds to a reduction in brightness by a factor of about 2.5. 10 magnitudes reduces the light by a factor of 10,000. In the densest filaments and cores of molecular clouds, the visual extinction can reach tens of magnitudes, sometimes hundreds. 100 magnitudes of extinction corresponds to a reduction in brightness by a factor so large that even the phrase 100 magnitudes fails to carry its full weight. A star 10 times brighter than the sun, sitting directly behind such a core, would be completely invisible, not faint, not reddened, but absent. Its light would be absorbed entirely before reaching the near side of the core. The result is what astronomers call a dark nebula. Against a field of background stars, a dark nebula appears not as a glowing cloud, but as an absence, a region where the stars simply stop. No special darkness, no visible boundary, just stars, 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 and then a place where there are none, the background light blotted out as thoroughly as if a piece of the sky had been replaced with something opaque. The shape of that absence traces the shape of the densest part of the cloud, the innermost architecture of the filaments and cores, made visible not by what they emit, but by what they block. The dark nebula, called Barnard 68, lies roughly 500 light-years from Earth, in the direction of the constellation Ophiuchus. It is a dense, cold molecular cloud core, roughly half a light-year across, containing roughly twice the mass of the Sun. Photographs of it show a nearly perfect dark oval against a rich star field of the galactic plane. Within that oval, the stars do not diminish gradually, as they would if the cloud were merely thin and absorbing. They simply cease. The edge of the dark region is sharp enough that stars can be seen right to its boundary, and then there is nothing. The core is optically thick at visual wavelengths, not transparent, not translucent, but opaque in the way a stone wall is opaque through a completely different physical mechanism, but with the same observable effect. This quality of absence, the way a dark nebula presents itself, not as a thing, but as a gap in things, gives these objects a peculiar visual character. They are among the few astronomical phenomena that impress not through what they show, but through what they conceal. The dramatic objects of the sky are typically radiant, glowing nebula, bright star clusters, the hot plasma of supernova remnants trailing luminous filaments across the dark. A dark nebula offers none of this. It offers only a silence in the distribution of stars, a stillness in the middle of the background field, a held absence that might, if the eye lingers on it, begin to feel like the thing itself. What the eye cannot see is the interior. Inside that dark opacity, the conditions described above prevail. Temperatures near 10 Kelvin, densities high enough for molecules to form and persist, dust grains drifting in a slow cold current of gas, each one carrying its mantle of ancient ice. The cold there is not recent. The dust there is not newly formed. The cloud has been assembling itself, drawing material together from the interstellar medium, organizing its structure under the competing forces of gravity and turbulence and pressure for tens of millions of years. Some of the material inside it has been cycling through the interstellar medium for billions of years, shed from stars that lived and died long before the sun formed, drifting as free atoms and small molecules through the diffuse interstellar gas before being swept up into this cloud's slow accumulation. The scale of a giant molecular cloud laid against the sky is not easily resolved by the eye alone. Most of them are too large and too diffuse to see as distinct objects in the way a star or a planet appears distinct. The Orion molecular cloud, one of the nearest and most studied, lying roughly 1,500 light-years away, extends across a region of sky more than 10 degrees wide, 20 times the width of the full moon. Its nearest active star-forming regions, the Orion Nebula and the region around it, are visible to the unaided eye on a dark night as a faint smudge in the sword of the Orion constellation. But that smudge represents only a small illuminated fraction of the total cloud, the region where newly formed massive stars have ionized the surrounding gas and made it glow. Most of the cloud is dark, cold, and invisible, extending far beyond the glowing nebula into the surrounding dark. From a sufficient distance imagined, since no telescope can step outside the Milky Way and look back with any resolution of individual clouds, a giant molecular cloud in a spiral arm would appear as a dark lane, a region of reduced stellar brightness where the accumulated dust blocks the light of background stars. The spiral arms of other galaxies, seen face-on, show these dark lanes clearly, dark bands running along the inner edges of the bright arms, where molecular clouds are concentrated, where star formation is most active, where the next generation of stars is already gathering in cold, dark cores. Within the Milky Way, several thousand of these clouds drift through the galactic disk. They form in the compressed regions behind spiral density waves, in the shells around old supernova remnants, in the regions where galaxy-scale flows of gas collide and cool. They persist for tens of millions of years before the stars they form, particularly the massive hot ones, begin to pour out radiation and stellar winds powerful enough to erode the cloud from within, dispersing the gas back into the interstellar medium, seeding the next generation of clouds with the elements forged in the stars that just died. The cloud, in this sense, is not a permanent feature. It is a temporary accumulation, a slow gathering of material that will eventually be dispersed by the very process it enables. But temporary on a galactic timescale means something different from temporary on a human one. A molecular cloud that forms and disperses over 50 million years has existed for 10,000 times longer than all of recorded human history. The cold inside it, the dust drifting through it, the slow chemical processes occurring on its grain surfaces, all of these have been proceeding in darkness and stillness for longer than complex animal life has existed on Earth. There is a texture to that duration that is hard to hold in a single thought. Not the duration of a human life, or a civilization, or the existence of the species, not even the age of the planet. The molecular cloud drifts through the spiral arm of the galaxy on timescales that encompass the entire evolutionary history of vertebrate life on Earth, from the first fish to the present, several times over. During all of that time, its interior holds at 10 Kelvin. Its dust grains accumulate their ice. Its dense cores press inward against the competing forces, trying to hold them at rest. And nothing announces this. No light escapes, no signal travels outward from the core to indicate that something immense is quietly occurring inside. The hierarchy of the cloud's internal structure, the nested architecture from diffuse envelope to core, develops over this same long timescale. What looks in any snapshot like a static arrangement of gas and dust is in fact a slow continuous churning, turbulent motions compressing gas here, allowing it to expand there, filaments forming and dissipating on timescales of millions of years. The structure is not frozen, it is slow, and the distinction matters because what looks like permanence at any moment is actually the frozen frame of a process that will, on its own terms, lead somewhere. A molecular cloud core at 10 Kelvin has no warmth to radiate. It glows only at wavelengths far longer than visible light, in the radio and millimeter range, in the faint emission of cold molecules and cool dust. To a human eye, it would be invisible in every meaningful sense. Even an infrared camera, sensitive to the near-infrared wavelengths that can peer through some dusty regions, would find the deepest cores opaque. Only at radio and millimeter wavelengths, where the dust becomes transparent, does the interior become legible. But legibility was not the original condition of the cloud. For the great majority of its existence, before any instrument could read it, before any eye could have been present to attempt the reading, the cloud simply was cold, dark, structured, chemical, drifting through the spiral arm at a few kilometers per second relative to the surrounding disk, turning very slowly with the galaxy, carrying its millions of solar masses of material in a darkness that was complete. The dust grains within it, each one a few nanometers to a micrometer across, each one composed of silicate or carbon or a mix of both, each one wrapped in its thin mantle of frozen water and carbon dioxide, drift in the interior without knowledge of their duration. They have been accumulating their icy coatings for millions of years. The outermost layer of a grain, deep inside a molecular cloud core, may have frozen onto the grain's surface only a few 100,000 years ago, in the astronomical sense recently. The innermost layers may be far older, mineral cores whose silicate structures were forged in the outflowing winds of a red giant star that died long before the sun was born, then released into the interstellar medium, then swept up into this cloud's slow accumulation, then coated over millions of years in the dark until the original mineral surface is hidden under a crust of ice. Many molecular layers thick. A single grain holding that history in its structure is too small to see. 10,000 of them, laid end to end, would reach only to the width of a human hair. And yet the cloud holds a number of them so large that the accumulated mass of all its dust, 1% of the total, equals tens of thousands of solar masses. The immensity and the smallness exist simultaneously at different scales of the same object, both equally real. The silence of a molecular cloud core is a physical condition, not a metaphor. Sound requires pressure waves in a medium. The molecular cloud has a medium gas, but the density of that gas is so low that the mean free path of any individual molecule, the average distance it travels before colliding with another molecule, is enormous. In the outer parts of the cloud, a single molecule may travel kilometers before it encounters another. Even in the densest core, the molecular density is low enough by the standards of anything familiar that the propagation of ordinary sound would be entirely negligible against the background thermal noise. The quiet of a molecular cloud core is the quiet of near vacuum, not the pressed-down silence of a soundproofed room, but the absolute quiet of a place where matter is too sparse to carry a disturbance from one point to another in any meaningful way. That silence has been the condition of the core for as long as the core has existed. The dust drifts. The molecules move in slow thermal currents at speeds consistent with their 10 Kelvin temperature, which for a hydrogen molecule is a few hundred meters per second, fast by human standards, but so much slower than the molecular speeds at room temperature that the interior of the cloud would feel, if kinetic energy could be felt directly, almost completely still. The thermal energy per molecule is tiny. Each molecule carries only a fraction of the energy that a molecule at room temperature carries. The cloud has no heat to share, no warmth to radiate, no light to scatter. It exists in the dark at 10 Kelvin, and it has done so for longer than there have been animals to imagine such a thing. Against the wide field of background stars that lie beyond it, stars belonging to the more distant parts of the galaxy's disk, or to the galactic bulge, or even to other structures farther still, the dense filaments and cores of the molecular cloud appear as shadows, not as darkness in a simple sense, because the background itself is not uniformly bright. The stellar field behind a molecular cloud is a scattered, irregular distribution of stars at many distances, each one a point of light, and against that distribution, the cloud's densest regions produce a silhouette, a region where the points of light simply cease, where the star field that continues on either side abruptly stops, where the eye, if it were looking, would find nothing. The shape of that silhouette is the shape of the cloud's interior density structure projected onto the plane of the sky. Filaments dense enough to block all background light appear as dark lanes, narrower than the surrounding cloud, threading through the star field in elongated shapes that trace the internal geometry of the structure. Cores appear as darker, more compact regions within those lanes, spots where the opacity is greatest, where the column of dust along the line of sight is deepest, where the extinction of light is most complete. The silhouette is, in this sense, a map, not of the cloud's surface, but of its interior, projected flat. The three-dimensional density structure collapsed into a two-dimensional shadow against the background light of the galaxy. That shadow has edges, not sharp edges in every case. The outer parts of the cloud are diffuse enough that the extinction is gradual, the star field thinning slowly as the line of sight passes through increasingly dense material. But at the core, the edge is sharper. The transition from visible star field to opaque darkness can occur over an angular distance, small enough that a star can be seen clearly on one side of the boundary, and nothing can be seen on the other. The material responsible for this abrupt transition is a column of dust a fraction of a light-year thick, thin by the standards of the cloud's full extent, but dense enough in that thickness to achieve an extinction so total that no photon of visible light can pass through it. Those photons, blue, green, red, the full range of visible wavelengths, enter the outer layers of the core. They are absorbed by the first dust grains they encounter. They do not re-emerge at visible wavelengths. They are reprocessed into the thermal emission of the dust, re-radiated at wavelengths many hundreds of times longer, where the dust is no longer opaque. The light from the stars behind the core does not accumulate behind the dust and wait for a gap, but it is absorbed, converted, and lost as visible light permanently. The stars behind a dense core are not hidden. They are, for any observer on the near side of the core, genuinely extinguished at wavelengths the eye can detect. What remains, facing that dark region, is only the absence, a silhouette that carries no information about what is behind it, a region of sky that looks as though nothing exists there, not because the universe is empty in that direction, but because the cloud is full enough of dust to make the stars beyond it invisible. The darkness is not vacuum. It is opacity. It is material. It is a cold, structured, ancient accumulation of gas and dust that has gathered itself over tens of millions of years into densities sufficient to block the light of the galaxy behind it, holding its interior at temperatures near the floor of what nature achieves, carrying in its dust the mineral legacy of dead stars, and existing completely, silently, without light, in the dark between the stars. The cloud does not glow, the core does not shine. The dust grains at 10 Kelvin emit radiation too cold and too long in wavelength for any human sense to receive. Against a star field, the densest regions appear simply as the sky from which the stars have been removed, shapes defined by what they prevent, silhouettes that persist for millions of years before any internal change begins to alter the opacity that makes them visible as absence. In the direction of the densest cores, the stars behind simply cease to exist for any observer on this side of the cloud, not dimmed, not reddened beyond recognition, absent. The light that set out from them millions of years ago, crossing the distance between that distant stellar surface and the near edge of the cloud, entered the dust and did not come out. The photons are gone. The stars continue to shine somewhere beyond the core into whatever space lies on the other side. But from here, in the shadow of the cold and the dust, the only thing visible in that part of the sky is the quiet, dark, vast, still, extraordinarily cold, and entirely at rest. 2 hydrogen atoms drift through the interior of a molecular cloud, moving at speeds only a little faster than the vibration of cold gas, a few hundred meters per second, in air that is almost no air at all. They are alone in a volume roughly the size of a room, separated from the next atom by a distance that would take light a fraction of a second to cross. In the cold gas of a molecular cloud, at temperatures barely above absolute zero, a collision between 2 lone hydrogen atoms happens perhaps once in a million years. And when they do collide, something happens that prevents the very thing that ought to follow. The energy released when 2 hydrogen atoms bind together has nowhere to go. In the open gas, there is nothing to absorb it. The molecule they almost became simply breaks apart again before it can settle, the bond forming and dissolving in the same instant, the 2 atoms departing unchanged. This is the problem at the center of everything. Molecular hydrogen is the most abundant molecule in the observable universe, the raw material from which stars and solar systems, and the long chain of matter that includes planets and weather and living things, all descend. And it cannot form an open space. Not efficiently, not without help. The universe built the most common molecule it contains through a process that requires something else entirely. Something smaller and older and slower than any star, something so modest that the eye passes over it without registering it at all. A dust grain lies in the cold interior of a molecular cloud, drifting through gas so thin that it collides with a molecule perhaps once every few years. It is not large. On one side of it, the grain could be measured in nanometers, several dozen atoms wide in its thinnest dimension. On the other, it stretches toward a micrometer, the width of a single bacterium seen through a microscope, a measure so small that a human hair contains roughly 60 of them laid side by side. The grain is old. It has been drifting in this cloud for millions of years, absorbing nothing, emitting almost nothing, cold all the way through to its silicate or carbon core. Its surface is rough and irregular, pitted with tiny hollows and ledges at the scale of single atoms, and into those hollows the atoms of the gas slowly settle. A hydrogen atom arrives at the grain's surface. It does not arrive quickly or with any particular force. It is simply moving through the gas at the speed of cold things, and the surface of the grain is there, and the atom settles into a shallow hollow in the grain's irregular face, the way water settles into a low place in stone. The temperature of the grain is perhaps 10 Kelvin, colder than the surface of Pluto, colder than almost anywhere in the solar system, and at that temperature, the hydrogen atom does not have enough energy to escape immediately. It stays. It waits. It migrates slowly across the surface of the grain, moving from hollow to hollow over timescales that might extend to thousands of years, because the grain is cold and the atom moves cautiously in the cold, each step a tiny thermal hop across the grain's rough face. Somewhere else on the same grain, another hydrogen atom settles in. It too begins to migrate, and eventually, across a surface no wider than a living cell, two migrating hydrogen atoms find each other. The bond forms. The energy of the bond goes into the grain itself, absorbed into its lattice of silicate or carbon, dissipated as a faint vibration that the grain slowly radiates away. The molecule departs, launched back into the gas with just enough energy to leave the surface, carrying its new bond with it into the cold interior of the cloud. This is how it happens, not through collision in open space, but through patience on a surface. Not in an instant, but over hundreds or thousands of years of slow migration across a grain no wider than a cell. The universe makes its most abundant molecule this way, grain by grain, one surface encounter at a time, over millions of years of dark and cold. And the grain does not stop there. Once the hydrogen has come and gone, other molecules arrive. Water molecules, or the atoms that will become them, find their way to the grain's surface and freeze there. Carbon dioxide settles on top of the water. Carbon monoxide arrives later, at colder temperatures still, and freezes onto the outermost layer. The grain builds up its icy mantle the way a stone in a cave accumulates mineral deposits, slowly, layer on layer, each species of molecule freezing at the temperature threshold where the gas can no longer hold it. Water ice forms first, nearest the grain's rocky core, then carbon dioxide, then, at the outermost surface where the temperature is lowest and the cold is deepest, carbon monoxide ice, the frost of the coldest places. Carbon monoxide ice, the frost of the coldest places. The grain becomes a layered object, silicate or carbon at the center, water ice above it, other ices above that, each layer a record of the temperature at which it formed, the whole structure no larger than a bacterium, and holding inside it a history of the cold. Telescopes have read these mantles, not by observing the grains directly. They are far too small and far too cold to see through any ordinary means, but by watching what they do to light passing through them. When a bright star lies behind a dense molecular cloud, its light passes through millions of dust grains on its way to an observatory, and each species of ice on each grain absorbs a particular narrow band of that light at a particular infrared wavelength. The result is a spectrum with dips in it, characteristic absorptions stamped into the continuum like a series of quiet marks. Water ice makes one, carbon dioxide makes another, carbon monoxide leaves its own. These dips were first detected by infrared observatories in the late 20th century, and with each new generation of instrument, they have been confirmed and extended. The inventory of frozen molecules growing richer and more detailed with each observation. The ice mantles are real. The layering is real. The cold grain drifting in the dark, coated in frozen water and frozen carbon dioxide and frozen carbon monoxide, has been measured, indirectly but clearly, across distances of hundreds of light years. But there is more happening on the surface of that grain than simple freezing. Hydrogen atoms arriving on an icy mantle can react with the molecules already there. Carbon monoxide on the grain's surface can accept a hydrogen atom and then another, and through a sequence of additions become formaldehyde, a molecule of one carbon, two hydrogens, and one oxygen, a simple arrangement of four atoms that is detectable at radio wavelengths in molecular clouds across the galaxy. Formaldehyde can accept more hydrogen atoms and become methanol, a slightly larger molecule, still simple, still built one atom at a time in the cold dark on the surface of a grain. These grain surface reactions happen slowly, across timescales of millions of years, driven not by heat, but by the slow arrival of reactants from the surrounding gas, and the reactions proceed at temperatures far too low for the same chemistry to occur in a liquid or a gas. The cold, paradoxically, makes certain things possible that warmth would prevent, because at low temperatures, the molecules that arrive at the grain's surface stay long enough to react, rather than evaporating away before the reaction can complete. The gas between the grains is not empty of chemistry either. Ion-molecule reactions proceed efficiently in the cold, low-density gas of a molecular cloud, driven not by thermal energy, but by the ionizing radiation that penetrates the cloud from outside, cosmic rays, high-energy particles moving at near light speed, passing through the cloud and occasionally stripping an electron from a hydrogen molecule or a helium atom, leaving behind a charged fragment that then reacts with neutral molecules in ways that a neutral atom never could. These reactions build complexity step by step. A protonated molecule reacting with a neutral one, the product of that reaction reacting with something else, the chain of steps producing molecules of 3 atoms, then 4, then 5, through pathways that are slow individually, but relentless collectively, operating continuously across volumes of molecular cloud material that dwarf any laboratory by factors too large to hold clearly in mind. Carbon monoxide forms this way, not on a grain surface but in the gas phase, through a chain of ion-molecule reactions that begins with cosmic ray ionization and ends with a molecule of 1 carbon and 1 oxygen bound in the strongest chemical bond in nature, drifting in the cold gas at 10 Kelvin, vibrating at a frequency determined by the masses of its 2 atoms and the strength of the bond between them. That vibration is the key, because a carbon monoxide molecule has an asymmetric charge distribution. It carries a small permanent electric dipole, and when it rotates from one energy state to a lower one, it emits a photon at a wavelength of approximately 2.5 millimeters, a wavelength invisible to the eye, deep in the radio spectrum, but detectable from the ground by radio telescopes in cold, dry places with the right receivers. The photon travels away from the cloud at the speed of light. If the cloud is moving, the photon's wavelength is shifted slightly from what it would be at rest, compressed a little if the cloud is approaching, stretched a little if it is receding, and that shift, measured precisely enough, tells the observer how fast the gas was moving when the photon was emitted and in which direction. This single rotational transition from the first excited state to the ground state of carbon monoxide has done more to map the molecular universe than almost any other measurable quantity. Cold hydrogen gas, which makes up the vast majority of every molecular cloud, emits no radio photons of its own at the temperatures found in cloud interiors, because hydrogen molecules lack the charge asymmetry that would allow them to radiate at low energies. They are invisible to radio telescopes in the cold. Carbon monoxide is not invisible. Carbon monoxide radiates readily at 2.5 millimeters, and because it is present everywhere that molecular hydrogen is present, tracing carbon monoxide is as close as astronomers can get to tracing the hydrogen itself. The maps it produces are not perfect. The ratio of carbon monoxide to hydrogen varies from place to place in ways that complicate interpretation, but across 40 years of radio surveys, those maps have revealed the structure of molecular clouds across the Milky Way and across other galaxies, tracing the filaments and clumps and voids that make up the interstellar medium, all from the patient collection of 2.5 millimeter photons arriving at cold antennas on high plateaus. A radio telescope pointing at a molecular cloud on a night with no wind receives a signal at that wavelength that is almost indistinguishable from the noise of its own receiver electronics. The signal from a molecular cloud 100 light-years away at a wavelength of 2.5 millimeters is measured in millikelvins thousandths of a degree above the ambient temperature of the receiver, and extracting it from the background requires careful calibration and long integration times, the antenna dwelling on the same patch of sky for minutes or hours, the signal accumulating slowly above the noise the way a faint image accumulates on a photographic plate in a long exposure. But the signal is there. It has always been there, moving through the galaxy at the speed of light, since the carbon monoxide molecule that emitted it rotated from one state to another in a cold cloud somewhere in the galactic disk, and finally arriving, after however many thousands or millions of years of travel, at a dish of metal on a cold, dry plateau where it is captured, amplified, and turned into a number. The molecular cloud that emits these signals contains more species of molecule than carbon monoxide, and some of them tell a deeper and more intricate story than any simple abundance map could convey. In the densest and coldest cores of star-forming clouds, and in the warm envelopes surrounding newly forming protostars, radio and millimeter wave spectroscopy has detected molecules of increasing complexity, molecules of 6, 7, 8 atoms, molecules that organic chemists would recognize as related to the substances found in living cells. Methanol has been detected in cold cloud cores. Formaldehyde has been found throughout the galaxy. Dimethyl ether, 2 methyl groups joined by an oxygen, has been identified in warm protostellar regions and in clouds that are close enough to be studied in fine detail by the most powerful radio telescope arrays on the planet. Even more complex species have been found, including glycolaldehyde, a molecule of 5 atoms arranged as a simple sugar, the first sugar-related molecule ever detected in a star-forming region, and ethylene glycol, and formide, each one a small, quiet argument for the richness of interstellar chemistry. These detections do not arrive easily. Each molecule has a unique rotational spectrum, a set of characteristic frequencies at which it emits or absorbs photons when its molecular bond lengths and angles and masses cause it to rotate from one quantum state to another. A molecule with more atoms has more rotational modes, more transitions, a denser forest of lines spread across the radio and millimeter spectrum, and identifying it in the spectrum of a molecular cloud requires matching the observed lines to laboratory measurements of the same molecule made at known temperatures and pressures. The laboratory work and the observational work have to proceed together, each informing the other, the astronomers looking for signals that the laboratory chemists have predicted, and the laboratory chemists extending their measurements to cover new molecules that the astronomers suspect might be present. The detections accumulate slowly, each one requiring careful elimination of alternative explanations, each one adding one species to the inventory of what the cold dark contains. The place where the most complex molecules have been found is not always the coldest, most quiescent part of a molecular cloud. It is often a region where a young protostar has already formed and is warming its immediate surroundings, releasing from their icy grain mantles the molecules that have been frozen there for millions of years. This warming happens gradually. As the protostar grows and its luminosity increases, the temperature of the dust in its immediate vicinity rises above the sublimation point of each molecular species. In turn, first carbon monoxide, which evaporates at temperatures around 20 Kelvin, then methanol and formaldehyde at somewhat higher temperatures, then water ice when the temperature reaches about 90 to 100 Kelvin. Each species enters the gas phase as the temperature reaches its threshold, and the gas phase abundance of each molecule spikes suddenly as the ice mantle of an entire population of dust grains releases its stored chemistry into the surrounding volume. These warm, chemically rich regions around newly forming protostars have a name that signals their character. A hot carino is a region no larger than the volume enclosed by the orbit of Neptune, heated by the protostar at its center to temperatures between 100 and a few hundred Kelvin, in which the gas phase abundance of complex organic molecules is elevated by 100 or 1,000 times relative to the cold cloud material surrounding it. The name distinguishes it from a similar but much larger structure found around more massive forming stars, the hot molecular core, which can span a volume larger than an entire solar system. But both are variations on the same theme, a warming interior releasing into the gas what the cold had stored in ice. In a hot corino, a radio telescope sensitive enough can detect dozens of molecular species, some of them simple, some of them complex, all of them distributed in a small bright region that stands out against the cold envelope like a warm lamp in a dark building. The warm region is small. It occupies a tiny fraction of the total volume of the molecular cloud in which the protostar is embedded. Around it, the cold cloud material continues as before, undisturbed, its dust grains still bearing their ice mantles, its gas still moving at the quiet velocities of 10 Kelvin matter, its carbon monoxide still rotating and emitting its 2.5 millimeter photons, as it always has. The chemistry of the warm region and the chemistry of the cold are different in kind, not just in degree. The gas phase reactions available at 100 Kelvin are unavailable at 10, and the surface reactions available at 10 Kelvin slow to nothing at 100. So the two regimes produce different molecules by different pathways, and a complete picture of what a star-forming cloud contains requires both. The cold chemistry builds the raw materials. The warm chemistry, when and if it comes, transforms them. In certain star-forming cores that have been studied at high resolution, something even more specific has been found. Phosphorus, the element that forms the backbone of DNA's double helix and carries the energy currency of every living cell, is detectable in molecular clouds in the form of two simple molecules, Pn, phosphorus and nitrogen, and Po, phosphorus and oxygen. These detections are not made in cold cloud cores, where phosphorus is likely frozen onto grain surfaces or locked in refractory grain material. They are made in the warm shocked gas around young protostars and in the outflow regions where jets from newly forming stars plow into the surrounding cloud material and heat it. In those shocked regions, the phosphorus chemistry is activated, and the two simple phosphorus-bearing molecules become detectable at millimeter wavelengths, their rotational lines appearing in the spectrum alongside the more abundant molecules of the surrounding gas. This is not a claim about life. It is a description of what has been measured. Pn and Po are not DNA, and they are not cells, and there is no chain of logic short enough to connect their presence in a shocked protostellar outflow to anything that will ever metabolize or reproduce. But they are there. Phosphorus is there, in a molecular cloud, in chemical form, in a region where dust and gas are assembling themselves into something that will one day be a star, and probably a disk of orbiting material in which solid bodies will form. What happens to the phosphorus between the molecular cloud and the solid bodies is a long and complicated and mostly unresolved story, one that has no clear ending yet. What the observations establish is simply that the element is present at the beginning, in the same cold chemistry that contains the water and the carbon monoxide and the methanol and the simple sugars, part of the same slow, patient inventory that the cold dark has been assembling on grain surfaces and in the gas for longer than the solar system has existed. The inventory has been extended most recently by an observatory whose sensitivity at infrared wavelengths exceeds everything that came before it by a factor that changes what can be seen. Since beginning its observations, the James Webb Space Telescope has turned its instruments toward molecular clouds and observed the absorption spectra of background stars through the intervening dust, and what it has found confirms and extends the earlier catalogs. Water ice, carbon dioxide ice, carboning monoxide ice, carbonyl sulfide, and in some observations, the possible presence of additional molecular species in the ice mantles, species that may require further analysis to confirm, the identification still in the careful process of verification that any new spectroscopic claim requires. The ice mantle inventory is not closed. Each new instrument adds new lines to the spectrum, and each new line represents another molecule frozen onto the surfaces of grains in a cold cloud, another small piece of the chemistry that the dark has been doing quietly, without observation, for a very long time. There is a quality to this chemistry that is easy to overlook when describing it at the level of molecules and reactions and spectral lines. It is happening everywhere, not in one cloud, not in one special region of one spiral arm, but in every molecular cloud in the galaxy. In every molecular cloud in every galaxy, across the full volume of the observable universe, in every direction and at every distance, in the cold gas between stars, wherever the density is high enough and the temperature is low enough for molecules to survive. The same grain surface reactions are occurring in the molecular clouds of the Large Magellanic Cloud and the Small Magellanic Cloud. The same carbon monoxide transition is emitting its 2.5 millimeter photons in clouds that formed stars 2 billion years before the solar system existed. The same ice mantles are accumulating on dust grains in clouds that will not produce a single star for another 10 million years. The chemistry is not a preparation for something. It is simply a feature of the universe, a consequence of the temperatures and densities and compositions that cold, dense molecular gas produces, the same way turbulence is a feature of rivers and erosion is a feature of exposed rock. It happens because the conditions for it exist, and the conditions exist everywhere the clouds exist. A single dust grain in the interior of a molecular cloud has been in the dark for a time longer than any one human civilization has existed, longer than any human civilization could exist. It drifts in the cold gas at speeds measured in fractions of a meter per second, below the pace of a slow walk. Its surface is coated in layers of ice that have not moved or melted or changed state in millions of years. In its outermost layer, at a temperature of 10 or 12 Kelvin, carbon monoxide molecules are locked into place, unable to evaporate, unable to react significantly with their neighbors, held in their frozen arrangement by a cold so deep and so absolute that the distinction between solid and gas barely seems to apply. Everything is frozen. The grain and its mantle and the gas immediately surrounding, it all existing in a kind of thermal equilibrium that is almost a form of stillness. The grain is a record of everything that has passed through the cloud since the grain formed. Every molecule that settled onto it and stayed, every bond that formed on its surface, every layer of ice that accumulated, all of it is still there, preserved in the cold, undisturbed. On its surface, somewhere in one of the shallow hollows of its irregular silicate face, a hydrogen atom is migrating. It arrived from the surrounding gas perhaps a century ago, settling into a low-energy site at the edge of the water ice mantle. And since then, it has been moving slowly from site to site, a thermal hop at a time, covering distances of a few atoms with each step. Somewhere else on the same grain, perhaps on the opposite side, another hydrogen atom has arrived more recently and has begun its own slow migration. Between them, at the temperature of 10 Kelvin, the distance is enormous and the time it will take to cross it. Perhaps thousands of years of slow migration before the two come close enough to find each other. When they do, the bond will form in a fraction of a second. The energy will go into the grain, the molecule will depart, and somewhere in the gas of the molecular cloud, a hydrogen molecule will be moving that was not moving before, the simplest and most abundant molecule in the universe, made by the most patient process the universe contains. On a surface no wider than a living cell, in a cold so deep and a dark so complete that no photon of visible light has passed through it in millions of years. In certain corners of the densest cloud cores, in regions where the chemistry has had the longest uninterrupted time to work, the ice mantles on dust grains carry molecules that organic chemists would find familiar in outline, if not in context, carbon and hydrogen and oxygen arranged in small structures, the beginnings of patterns that appear much later in the chemistry of warmer and brighter places. Not life, not even the building blocks of life in any direct sense, since many steps and much transformation lie between a frozen grain in a cold cloud and anything that metabolizes, but a real chemical complexity built one bond at a time on cold surfaces and in cold gas, preserved in ice across timescales that dwarf anything human experience can easily anchor to. The dark has been doing this work far longer than the sun has been shining. In the cold interior of every molecular cloud, on every dust grain that drifts through the quiet gas, the chemistry continues, slowly, without warmth, without light, without anything pressing it toward an outcome, and the inventory of what the dark contains grows, molecule by molecule, in the old and patient silence. At the center of a cold molecular cloud core, In a region of space where the temperature sits somewhere near 10 degrees above absolute zero, a clump of gas has been still for a very long time. Not still in the way a room is still when no one moves through it. Still in the deeper way of something that has no mechanism for change, no gradient to follow, no force yet strong enough to set it moving. The clump drifts, it rotates, barely. Its outermost layers press gently inward against the pressure of its own gas, and the pressure pushes back, and the two forces sit balanced against each other in a suspension that has lasted, in some cores, for several million years. That balance has a threshold. James Jeans, working at the turn of the 20th century, worked out the mathematics of when a gas clump will hold and when it will fall. The number he arrived at, the critical mass below which thermal pressure wins and above which gravity wins, is not an abstraction. It is a real threshold, written into the physics of the gas, and in a core chilled to 10 Kelvin at the densities found in the densest molecular cloud material. That threshold works out to somewhere between 1 and 2 times the mass of the Sun. It is a quiet coincidence, or perhaps not a coincidence at all, that most of the stars that form in these clouds arrive with masses close to that same number. The physics of the cold predicts the population of the galaxy in a rough and patient way. Gravity is always present. It never stops pulling. In a stable cloud core, the gas pressure is simply larger, molecule by molecule, than the gravitational pull trying to draw the gas inward, and so the core rests. What changes is the ratio. As a core accumulates mass from the surrounding gas flowing slowly in from the cloud, as turbulence compresses a region briefly into a denser state, as the temperature drops just a fraction further in a shielded interior, the balance tips. Not in an instant. The tipping is gradual, the way a weight placed on one side of a scale shifts the whole thing by degrees before the pan finally descends. The core does not know it is collapsing. There is no moment of decision. There is only the quiet accumulation of mass and the equally quiet strengthening of a gravitational pull that eventually, over hundreds of thousands of years, becomes larger than the pressure holding the core open. When the infall begins, it is slow beyond any ordinary sense of slow. A parcel of gas at the outer edge of a collapsing core, falling freely under the gravity of the cloud, would take on the order of 300,000 to 500,000 years to reach the center under ideal conditions. In the actual molecular cloud, where magnetic fields and turbulence and thermal pressure slow the infall further, the true collapse extends over several million years. That is longer than the time that separates the present from the first members of the genus Homo. It is longer than the existence of most species that have ever lived on Earth. And the cloud core is not hurrying. It falls at the pace the physics allows, and no faster. The gas at the very center falls farthest and fastest. Infall is not uniform. The central regions collapse first, and the outer shells follow behind, raining down into a deepening gravitational well. As the central density rises, the core grows warmer. In the earliest phases of collapse, the gas is able to radiate the heat of compression away. The photons escape freely into the surrounding cloud, and the core remains cold, collapsing in what physicists call an isothermal regime. The temperature stays nearly constant. The infall continues. There comes a point, deep in the collapse, when the central density has risen to roughly 10 billion particles per cubic centimeter, a number that would be a near vacuum by any industrial standard, but that represents for a molecular cloud an extraordinary concentration of matter. At that density, the gas at the center becomes thick enough that its own infrared radiation can no longer pass through it freely. Photons are emitted and immediately reabsorbed. The heat of compression begins to build. The core, for the first time, stops being able to cool itself at the rate it is being compressed, and the temperature starts to rise. This transition from transparent to opaque, from isothermal to adiabatic, marks the birth of something new inside the collapsing cloud. The central region, no longer able to radiate away its heat, inflates against the infall. The pressure of the hot gas halts the collapse, at least temporarily, and what forms is a small, warm, quasi-stable object suspended at the center of the still infalling cloud. It is called the first hydrostatic core. It is not yet a star. Its temperature is measured in hundreds of Kelvin rather than the millions of Kelvin needed for nuclear fusion. Its radius is perhaps comparable to the distance between the Sun and Jupiter. Not a star, but a warm seed, a puff of gas suspended in freefall, holding itself open against the weight of everything still raining down on it from above. The first hydrostatic core is brief. The infall continues, and with it the pressure on the core's surface continues to grow. The temperature inside rises further. At around 2000 Kelvin, something happens to the molecular hydrogen that makes up most of the core's gas. The hydrogen molecules, which have been storing energy in their vibration and rotation without raising the temperature much, begin to dissociate. They break apart. And this dissociation absorbs energy, absorbs it efficiently, hungrily, pulling the thermal energy out of the gas before it can build pressure to resist the infall. The core's pressure support collapses for a moment, and the infall resumes with sudden force. The second collapse is faster and more violent than the first. The central region falls inward again, the density rising, the temperature climbing steeply until the hydrogen is fully dissociated and then ionized, and the gas is opaque and hot and resisting compression with the full force of a true stellar interior. A protostar has formed. Its nuclear fires are not yet burning, but the collapse has created something that is genuinely stellar in character, dense, hot, supported by thermal pressure, and radiating energy from the heat of its own formation. The protostar is invisible. It sits at the center of a dense, infalling envelope of cold molecular gas and dust, a shroud hundreds of times thicker than the gas it has already gathered into itself. The heat it radiates is absorbed by the surrounding envelope and re-emitted at much longer wavelengths. At visible wavelengths, there is nothing to see. The cloud is as dark as it ever was, and within it, the first true stellar embryo is buried without any outward sign of what has occurred. The transformation from cold core to hot protostar happens in silence and obscurity, in a place light cannot reach. What does escape the cloud is different from light, from the polar regions of the newly formed protostar. Moving perpendicular to the plane of the infalling material, narrow jets of plasma begin to emerge. They are fast, tens of kilometers per second at their base, accelerating in some systems to hundreds of kilometers per second as they travel outward. They are collimated, meaning they remain narrow and focused over great distances, extending outward from the source for distances measured in light years before they finally slow and spread into wider shock fronts. Nothing in ordinary experience quite matches the image. Two pencil-thin streams of hot ionized gas punching outward in opposite directions from a point of warm light buried inside a dark cloud, traveling for a year of distance every few decades, pressing through the molecular gas of the surrounding cloud and lighting up the material at the impact points in infrared and visible glows. The mechanism that produces these jets is not fully resolved, but the broad picture is one of magnetism and rotation working together. The infalling gas that cannot fall directly onto the protostar because it carries angular momentum and must orbit rather than fall straight in, settles into a flattened rotating structure around the protostar's equator. This is the accretion disk, and it is threaded with magnetic field lines that are dragged inward by the infalling material and wound by the disk's rotation into a tight helical configuration. Along the rotation axis, where the disk is thinnest and the field lines thread upward and downward away from the disk plane, the twisted field configuration can fling material outward at high velocity. The jet is, in a rough sense, the angular momentum of the infalling gas being paid out in another direction, concentrated and expelled at the poles, while the material itself spirals inward along the disk plane. The jets carry energy far from the protostar. They punch into the surrounding molecular cloud and push the cloud material aside, carving out cavities in the infalling envelope, creating bow shocks where the jet material slams into the slower gas ahead of it. These shocks glow. They emit light at wavelengths the eye can sometimes see, and at infrared wavelengths that penetrate the dust. A protostar that produces strong jets can be detected even when the protostar itself remains completely hidden, because the jets announce its presence through the glowing structures they carve into the surrounding cloud. The shocks are asymmetric and variable. The jet from one pole may be stronger or more energetic than the jet from the other, and the jets can precess, carving curved or sinuous paths through the cloud over time. The outflows driven by young protostars are not only jets. Around the narrow jet at wider angles, molecular outflows carry cooler entrained gas away from the protostar at lower velocities, tens of kilometers per second rather than hundreds. These molecular outflows sweep up cloud material, push it aside, and eventually play a role in dispersing the infalling envelope around the protostar. In a sense, the protostar begins to clear its own environment, almost from the moment it forms. The infall and the outflow exist simultaneously, material raining inward from the outer envelope, while other material is being driven outward through the polar cavities. It is a dynamic balance, one that continues for 100,000 years or more, while the protostar is still in its earliest embedded phase. The disk that forms around the protostar during this same period is the product of a simple physical constraint. The molecular cloud core from which the protostar formed was rotating slowly, almost imperceptibly, but rotating. A cloud core 10,000 astronomical units across rotating at even a tiny angular velocity carries angular momentum, and angular momentum is conserved. As the core collapses, the rotation must speed up in proportion to the decrease in scale, the same way a figure skater draws their arms inward and spins faster. The gas that falls inward and retains enough angular momentum cannot fall all the way to the protostar's surface. It reaches a radius at which its orbital velocity balances the inward pull of gravity, and there it settles into a circular orbit. Successive parcels of infalling material settle at similar radii. Over thousands of years, these parcels build up a continuous flattened structure, a disk. A protostellar disk is thin relative to its width. Its vertical extent, perpendicular to the orbital plane, is only a small fraction of its radius, because the gas in the disk is pressed flat by the disk's own self-gravity and by the dynamics of the orbital motion. In the vertical direction, the gas is supported by thermal pressure against the pull of the protostar's gravity. In the horizontal direction, it orbits. The combination produces a rotating, flattened structure that ranges in size from a few astronomical units in the smallest systems to over 100 astronomical units in the largest. A disk whose outer edge, in the largest examples, would extend considerably beyond the distance from the Sun to its outermost planets. Within the disk, gas and dust orbit the central protostar. The orbits are not uniform. Material closer in orbits faster. Material in the outer disk orbits more slowly, in accordance with the same gravitational law that governs the planets. This differential rotation creates shear in the disk, and through that shear, various mechanisms, viscosity, magnetic instabilities, gravitational interactions in a sufficiently massive disk transfer angular momentum outward through the disk, while material spirals slowly inward toward the protostar. The accretion disk is not static. It is a structure through which material flows, a river of gas and dust, moving from the infalling envelope into the disk, and from the disk's outer regions into the protostar's surface over tens of thousands of years. The dust in the disk begins, from the very first moments, to settle toward the disk's midplane. Dust grains drift downward through the gas, settling under the protostar's gravitational pull into a thin layer at the disk's center. The gas remains more extended, but the dust concentrates. This settling is the beginning of a longer process, not one that belongs to this early phase, where the protostar is still accreting and the disk is still being built from infalling material, but a structural tendency already present in the earliest disks, a kind of slow preparation for what will follow when the infall eventually stops and the disk finds itself alone around a young star. The protostar at the center of all this is growing. Each parcel of gas that falls from the disk onto the protostar's surface releases gravitational energy, and this energy heats the protostar and powers its luminosity. A protostar's luminosity in its early phase comes almost entirely from accretion, from the kinetic energy of infalling material being converted to heat at the surface. Nuclear fusion has not yet begun, and the protostar is not yet hot enough at its center to ignite hydrogen fusion, which requires temperatures in the tens of millions of Kelvin. Instead, it shines on the energy of its own collapse, a temporary and diminishing source that will sustain it only for as long as the disk continues to deliver mass. The surrounding infalling envelope grows thinner as accretion proceeds. Material that was once part of the cold molecular cloud core, hovering at 10 Kelvin, serenely undisturbed, has been drawn inward, accelerated by gravity, heated by compression, and added to either the disk or the protostar. The envelope is not destroyed uniformly. The jets and molecular outflows carve open cavities in the polar regions, and material preferentially falls in along the equatorial plane where the disk channels it. Gradually, over a timescale of roughly 100,000 years, the densest phase of protostellar accretion winds down. The infalling envelope is depleted. The protostar, though still deeply embedded in dust, is no longer surrounded by a thick rain of infalling cloud material. What remains at the end of this phase is a young protostar surrounded by a disk of gas and dust, a structure that sits at the threshold between the deep buried past and the more open future. The disk is the only surviving record of the cloud core from which everything began. The molecular cloud that once spanned light years has condensed, clump by clump, into this thin rotating plane, no thicker across its vertical extent than a small fraction of its radius, a memory of diffuse cold gas pressed into orbit around a new hot center. There is a way to think about what the disk carries with it. The angular momentum in the disk, the spin encoded in every orbiting parcel of gas, was present in the original cloud core as a faint, almost undetectable rotation. The cloud core rotated once on its axis every few million years or so, at most. That rotation, spread across 10,000 astronomical units of cold gas, was a whisper of motion, barely distinguishable from stillness. But as the cloud fell inward, that whisper was amplified by the mathematics of conservation: smaller, faster, preserved. The disk is the amplified echo of the cloud's original spin, concentrated and made real. Every orbit in the disk is a transformed version of the original cloud's slow turning. The cloud did not lose its rotation, it gave it to the disk. The jets emerging from the protostar's poles, meanwhile, continue their outward travel long after the most active phase of protostellar accretion begins to decline. They push into molecular cloud material that has no knowledge of the protostar that produced them. The cloud does not respond quickly to anything. Its crossing time is measured in millions of years. But the jets deposit their energy into the surrounding gas, stirring it, compressing it in the walls of the cavities they carve, and perhaps in some cases, triggering the compression of nearby dense regions enough to nudge them over the gene's threshold. A star being born may, through the energy of its jets, play a small role in the birth of another star at some later time. Though the chain of causation spans millions of years and cannot be traced in any single observation, the molecular cloud, for its part, continues to exist around all of this. The birth of a single protostar changes almost nothing about the large-scale structure of the cloud. The cloud is vast, 50 to 300 light-years across, containing the equivalent of hundreds of thousands to millions of solar masses of gas, and a single collapsing core represents a tiny perturbation in its overall structure. The cloud goes on being cold. Its outer regions remain at temperatures between 15 and 30 Kelvin. Its dense inner filaments stay opaque to background starlight. Other cores within the cloud continue their slow drift, some of them edging toward the gene's threshold on their own timetables, some of them held back by magnetic fields and turbulent pressure for millions of years longer. What the collapse of one core does alter, in a local way, is the chemistry and kinematics of the material immediately around the newborn protostar. The jets heat and compress the surrounding gas. The outflow cavities allow radiation from the protostar to escape into the surrounding envelope along the polar directions, warming material that would otherwise have remained cold. The molecular gas in the walls of these cavities can reach temperatures that would be extraordinary by cloud standards, hundreds of Kelvin, enough to release molecules from the ice mantles of dust grains and drive chemical reactions that do not occur in the undisturbed cold. The cloud is not uniform in its chemistry. The regions around young protostars are chemically enriched compared to the quiescent surrounding material, warmed and stirred by the very objects that formed within them. The accretion disk continues to change through all of this. In its earliest phase, it is massive, containing a significant fraction of the protostar's own mass, in some cases, and gravitationally unstable, prone to developing spiral arms and clumpy density structures as different regions of the disk collapse under their own gravity while the whole disk orbits. These gravitational instabilities can transport angular momentum efficiently, helping the disk deliver material to the protostar and helping the protostar grow. As the disk ages and the accretion from the envelope slows, the disk becomes less massive relative to the protostar, and the gravitational instabilities weaken. The disk enters a calmer phase, orbiting more smoothly, its structure determined increasingly by the slower processes of magnetic turbulence within the disk gas, rather than by the dramatic large-scale gravitational writhing of its youth. The protostar inside the disk keeps a slow interior fire, the heat of its own contraction, working through layers of gas that are still not hot enough at the center for nuclear fusion. The center is being compressed, slowly, by the weight of the layers above it. As the center grows hotter, the rate of energy loss from the surface can exceed the rate of energy production from accretion, and the protostar must contract further to supply the energy it is losing. This slow contraction phase continues for a very long time in low-mass protostars, hundreds of thousands to millions of years, a patient waiting for the moment when the central temperature reaches the ignition point. Before that moment arrives, the cloud core from which the protostar formed has been almost entirely consumed or dispersed. The infall has stopped. The disk, stripped of its supply from above, begins to evolve on its own. The boundary between the embedded protostellar phase and what follows is not sharp. The envelope thins gradually, the accretion slows, the disk transitions from an actively fed structure to a self-contained one. But at some point, the surrounding molecular cloud material is gone, and the system is exposed, a young star, not yet burning hydrogen at its core, surrounded by a disk of gas and dust that is the transformed remnant of a cloud core that once stretched across distances measured in light months. This transition is the edge of a long chapter. The cloud gave everything it had to build the disk, and the young star at its center. The cloud core's rotation became the disk's orbital motion. The cloud core's temperature, nearly zero, barely a whisper above absolute zero, became, through the violence of gravitational collapse, the heat at the protostar's surface. The cloud core's dust, the tiny silicate and carbon grains that drifted through the dark for millions of years, with ice mantles formed one molecule at a time, is now orbiting in the disk's midplane, settling layer by layer, being carried inward toward the star, or remaining in the outer disk. The disk is the cloud's last form, before it becomes something else entirely. It holds for a time the memory of everything the cloud was, cold, diffuse, slowly rotating, threaded with chemical complexity built up in the dark. The disk is smaller than the cloud by many orders of magnitude. It is thousands of times warmer near its inner edge than the cloud was at its core. It moves with a speed and purposefulness, every parcel on a determined orbital path that the cloud never had in its vast drifting stillness. And yet the disk is the cloud transformed. The same mass concentrated, the same angular momentum, encoded in every orbit, the same molecules, water and carbon dioxide and carbon monoxide, and the more complex organic species that assembled themselves on grain surfaces in the cold, carried forward into a new environment, some of them surviving the journey intact, frozen in grain mantles in the outer disk where the temperature is low enough to keep them from sublimating. The collapse of a cold molecular cloud core into a protostar and its surrounding disk takes several million years from the first inward motion to the dispersal of the infalling envelope. This is short by the standards of stellar lifetimes. A star like the Sun will live for 10 billion years, but long by any measure that means something to ordinary experience. The entire span of recorded human history is a small fraction of even the collapse timescale alone, and yet the collapse feels in retrospect swift. It is swift compared to the time the cloud core spent simply existing, drifting through the molecular cloud without changing, balanced between thermal pressure and gravity for millions of years before the balance finally tipped. A long stillness, and then a slow falling. That is the shape of stellar birth. The stillness is the cloud core in its undisturbed state, cold, dark, suspended. The slow falling is the collapse, and within the collapse, the formation of the first hydrostatic core, and then the true protostar, the emergence of the jets, and the settling of the accretion disk. Nothing happens quickly. Even the fastest events in this sequence, The second collapse triggered by hydrogen dissociation, the formation of the first hot central object, unfold over years and decades, which is fast by astrophysical standards, but remains entirely beyond the timescale of any direct observation. Every image of a protostellar system is a frozen moment in a process that spans millions of years. The observers on Earth who collect these images are seeing the state of a particular system at a particular moment in its long unfolding, unable to watch it evolve in any direct sense, working from the ensemble of many systems at different stages to piece together the sequence that no single observation can show in full. The disk, when the envelope is finally gone, sits in space around a young star and carries within it the structure of what came before. The cloud's long, cold silence is over. What the disk holds is warm at its inner edge, cold at its outer edge, a gradient of temperature that stretches from the near-stellar warmth inward to the cold of the outer disk, where the temperature in some systems barely climbs above 30 or 40 Kelvin, close to the temperature the cloud core once maintained throughout its entire interior. The outer disk is in this sense the last remnant of the cloud's cold. It carries the cloud's temperature, the cloud's chemistry, the cloud's ice-mantled grains, preserved in the orbital cold of a region far enough from the young star that the heat has not yet reached it. There is something in the geometry of the disk that speaks to what the cloud was. The cloud was vast and diffuse, extending across distances a light year would not contain. The disk is compact and structured, no larger across than a small fraction of a light year, but the shape of the transition, wide, diffuse material falling inward and concentrating into something flat and ordered, mirrors the shape of the cloud's own internal structure, its outer diffuse envelope giving way to denser clumps, clumps giving way to filaments, filaments narrowing into dense cores, the cores narrowing further still into the compact object at the center of the disk. The cloud organizes itself across a range of scales. The disk is the final step in that organization, the most concentrated and ordered form the cloud ever takes before it becomes something else. And then the accretion disk is alone. The infalling cloud material is gone. The jets are quieting. The protostar at the disk's center is contracting slowly toward its nuclear threshold. The disk will evolve for millions of years more before any further transformation occurs, its gas slowly accreting onto the star, its dust slowly settling and gathering into larger bodies, the long, unhurried process working through all that the cloud gave it. But the cloud itself, that vast, cold, patient structure that held the potential for all of this in its near-zero Kelvin interior, is no longer present as such. Its core collapsed. Its mass was gathered in. What remains of it, if anything, is the tenuous outer envelope, dispersed back into the molecular cloud from which it originally condensed, rejoining the larger structure of gas and dust that drifts through the galaxy's spiral arm on its own slow journey. The disk turns. The young star inside it warms toward the moment when it will sustain itself. The outer disk is cold, almost cold enough to match the temperature of the core from which the whole system descended. The ice on the grain surfaces in the outer disk. Water, carbon dioxide, carbon monoxide, the frozen remnants of millions of years of dark chemistry, is still present, still frozen, preserved in the shadow of the disk's midplane, where the star's warmth has not reached. The cloud gave everything it had. The disk holds what it gave. In the turning of the disk, cold at its edges and warm at its center, the cloud's long stillness finds its continuation, not as stillness anymore, but as orbit, as structure, as the slow, patient motion of a thing that will, given enough time, become something else entirely. A magnetic field line runs through the interior of a molecular cloud, the way a current runs through still water, present, shaping everything it touches, visible to nothing with eyes. The field does not glow. It does not vibrate at any frequency the body could feel. It is measured in microgauss, a unit so small that the Earth's own field is roughly 1,000,000 times stronger, and yet inside the vast cold dark of the cloud, this thread of invisible force is among the most consequential things present. It holds, it resists, it shapes which parts of the cloud will one day become stars, and which will remain cold gas for tens of millions of years, drifting through the spiral arm of the galaxy without ever finding the density needed to collapse. The geometry of such a field is not simple. On the largest scales, threading an entire giant molecular cloud from one edge to the other, the field lines run in organized patterns, loosely parallel, curving gently with the overall shape of the cloud, as coherent in their arrangement as the lines drawn around a bar magnet on a sheet of paper scattered with iron filings. The filings, in a real molecular cloud, are the dust grains themselves. Elongated dust grains slowly align their long axis perpendicular to the local field, spinning down through collisions with gas until their rotation matches the field geometry, and so the polarization of the faint infrared and submillimeter light they emit maps the direction of the field, invisibly threading the gas around them. This is how the field is read, not by detecting the field itself, which cannot be seen, but by reading the orientation of 10,000 tiny grains that have arranged themselves in response to it, like a landscape of grass flattened by a wind that has since gone still. Closer in, moving from the diffuse outer envelope of the cloud toward its denser inner regions, the geometry of the field becomes more complicated. Turbulent motions in the gas drag the field lines along, bending and tangling them. Where dense filaments of gas have accumulated, the field often runs perpendicular to the filament's long axis, as if the gas has fallen along the field rather than across it. In the densest cores, small regions a fraction of a light year across, where collapse toward a protostar is imminent or already underway, the field lines appear to be drawn in toward the center in an hourglass shape, pinched by the weight of the material pulling inward. The field does not yield easily. It bends, and the bending stores energy, and the energy pushes back against the collapse. The strength of a magnetic field relative to the mass of the gas it threads determines, more than almost anything else, whether a given piece of a molecular cloud will form stars or not. The critical quantity is the ratio of the cloud's mass to the total magnetic flux passing through it. Below a certain threshold, the magnetic pressure is sufficient to hold the gas against its own self-gravity indefinitely. The cloud is said to be subcritical in this case, supported, stable, unable to collapse no matter how long it waits. Above that same threshold, gravity wins. The cloud is supercritical, and collapse is not merely possible, but given enough time, inevitable. The star-forming cores that have been studied most carefully are found to be slightly above that threshold, not by a large margin, just enough that gravity, given sufficient time, can pull them inward against the resistance of the field. The resistance is real and prolonged. Even in a supercritical core, the magnetic field does not simply vanish or step aside. The gas must find a way past it, and the way it does is through a process so slow and so subtle that nothing about it would be detectable in any single human lifetime, or any 100 human lifetimes, or any 1,000. The process works because the gas in a molecular cloud is not a single substance, but a mixture of neutrals and ions. Neutral molecules, hydrogen, carbon monoxide, water, The vast majority of what is there have no electric charge. Ions, which carry charge and are a small fraction of the cloud, are tightly coupled to the magnetic field, locked to the field lines the way beads are locked to a wire. The neutrals are not locked. They respond only to gravity and pressure, and over immense stretches of time, they slowly drift inward, moving through the ion field lattice the way a current of water moves through a bed of reeds, not sweeping it away, but passing through it, molecule by molecule, grain by grain. The ions feel the drag of the neutrals passing by and pull on the field lines. The field lines resist, flex slightly, and allow the neutrals through. The magnetic flux does not move with the mass. The two gradually separate, mass accumulating at the center, flux remaining spread across the larger volume, and the core's mass-to-flux ratio rises, slowly, until gravity has what it needs. This separation is called ambipolar diffusion. It is estimated to operate on a timescale roughly 10 to 20 times longer than the freefall time of the cloud, something on the order of 10 million years in a dense molecular cloud core, meaning the core must wait, held in place by the slow resistance of its own magnetic field, for a span of time equivalent to twice the age of the most ancient rocks on Earth, before the neutral gas has drifted inward, far enough for collapse to proceed freely. The universe does not rush these things. The silence of that waiting does not mean the interior of the cloud is still. It is not still. On every scale, from the smallest resolvable structure to the full extent of a giant molecular cloud complex, the gas is in motion. The motions are not gentle. They are supersonic, moving several times faster than the speed of sound in the cold gas, which at 10 Kelvin is barely a fifth of a kilometer per second. To be moving supersonically in such a cold medium is to be moving at speeds of 1 to several kilometers per second, which sounds slow in comparison to a spacecraft or a bullet, but through gas as cold and thin as this, it is the equivalent of a sustained storm across the entire interior of the cloud. If the cloud were an unmagnetized gas, this turbulence would be destructive. Supersonic turbulent motions dissipate their energy quickly in shocks, collisions between fast-moving regions and slower ones that heat the gas and radiate the energy away. And in a medium with no magnetic field and no energy source, the turbulence would decay in a single crossing time. The time it takes a turbulent eddy to travel from one side of the cloud to the other. For a giant molecular cloud, several hundred light-years across, one crossing time might be on the order of a few million years. Without replenishment, the turbulence would go quiet. The thermal pressure alone would be insufficient to support the cloud, and the whole structure would collapse in a free-fall rush. The stars formed this way would be far more numerous and far more rapid than what is actually observed. The real universe makes stars slowly and selectively, not in one great simultaneous burst. A supersonic turbulent eddy passing through the cold interior of a molecular cloud looks, in the imagination, something like this: a region of gas several light years wide, moving at 3 or 4 kilometers per second, sliding through the surrounding material, which is itself moving, but in a different direction and at a different speed. Where the fast-moving region meets the slower one, a shock front forms. The gas ahead of the shock is cold, thin, and gently drifting. The gas behind the shock has been compressed and slightly heated, its density raised by a factor of several in the span of a thin boundary layer no wider than the mean free path of a molecule. A dense filament of compressed gas forms in the wake of the shock. If the filament accumulates enough mass quickly enough, it may exceed the critical threshold for gravitational collapse, and a protostar will eventually form there. If it does not, the turbulence that compressed it will also tear it apart before gravity can win, and the gas will disperse back into the surrounding medium, its brief density spike erased, contributing instead to the general churning that characterizes the cloud's interior. This dual nature of turbulence, simultaneously supporting the cloud against global collapse and locally compressing material into star-forming overdensities, is one of the central tensions of the molecular cloud. Turbulence both prevents stars from forming and creates the conditions in which they can form. It holds the cloud up while also punching pockets of dense gas into the genes and stability. The whole cloud persists in a kind of dynamic balance between these competing effects, never collapsing all at once, never dispersing entirely, but slowly and patchily converting a small fraction of its gas into stars over the course of several million years. The numbers confirm this balance. A typical giant molecular cloud, containing the equivalent of 1 million solar masses of gas, converts only about 1 to 3% of that mass into stars per freefall time. In absolute terms of 1 million solar masses of available gas, perhaps 10 to 30,000 solar masses ultimately become stars in any given freefall period. The rest remains gas, waiting, compressing, and decompressing in the turbulent flow, threaded by magnetic fields that slow its infall, drifting through the cloud without ever finding the conditions needed to collapse. The universe is a place of extraordinary restraint in this regard. The molecular cloud does not pour itself into stars. It resists, withholds, and transforms only a small portion of what it holds. Part of what sustains the turbulence against decay is the star formation that has already begun within the cloud. Young protostars, buried deep in their envelopes of infalling gas, launch bipolar jets and molecular outflows, streams of fast-moving material that punch outward from the protostar along its rotation axis, carrying momentum and energy into the surrounding cloud. These outflows travel at tens to hundreds of kilometers per second, far faster than the turbulent speeds of the surrounding gas, and when they interact with the ambient molecular material, they drive shocks that stir the cloud, compress nearby gas, and deposit kinetic energy back into the turbulent reservoir. A single protostellar outflow can inject enough mechanical energy into its immediate surroundings to influence the dynamics of the local cloud material for millions of years after the outflow itself has faded. Over the entire population of young stellar objects forming within a molecular cloud, these outflows represent a significant energy source, enough in some estimates to account for a substantial portion of the turbulent energy that keeps the cloud from collapsing globally. The newborn stars are, in a sense, helping to sustain the very conditions that slow the formation of their neighbors. Not through any intent, the jet does not know the cloud, and the cloud does not feel the jet as anything other than a pressure, but through the ordinary physics of energy transfer in a turbulent medium. The act of one star being born may delay the birth of the next one by millions of years. The magnetic field participates in this energy transfer as well. Where the field is strong enough, disturbances do not simply dissipate but propagate. They become waves. A perturbation in a magnetized gas sets the field line oscillating, and the oscillation travels outward along the field at a speed determined by the field strength and the gas density. These magnetohydrodynamic waves are called Alfvén waves, after the Swedish physicist Hannes Alfvén, who first described their behavior in the middle of the 20th century. In a molecular cloud, the Alfvén speed is typically 1 to several kilometers per second, close enough to the observed turbulent velocity dispersions that the two are nearly indistinguishable in many observations. What this means is that the turbulence in a molecular cloud is not a purely hydrodynamic phenomenon. It is magneto-hydrodynamic, threaded with wave energy that propagates along the field lines, carries tension through the cloud, and resists the dissipation that would otherwise drain the turbulent reservoir quickly. An Alfvén wave, traveling through the cold interior of a molecular cloud, carries no visible light. It produces no heat that would glow in any band of the spectrum. It is a wave of displacement. The field line bends away from equilibrium. The magnetic tension pulls it back, and the restoring force overshoots, setting the line oscillating. The gas parcels attached to the field move with it, rocking gently back and forth around their equilibrium positions, and the wave carries both field energy and kinetic energy at once, coupled together, propagating outward from wherever the disturbance originated, from a supernova remnant expanding into the edge of the cloud, from a stellar wind off a nearby massive star, from the shear of a giant molecular cloud drifting through the galactic disk. Energy enters the cloud from the outside at large scales, cascades down through smaller and smaller turbulent eddies, and is eventually dissipated, but more slowly and at smaller scales, and with more opportunity to compress dense gas into star-forming cores than it would be without the field to carry it. The cascade is not uniform. In a purely turbulent fluid, energy moves down a well-defined hierarchy from large eddies to small ones in a regular scale-free manner. In a magnetized medium, the cascade is anisotropic. It proceeds differently along the field lines than across them, transferring energy more efficiently in the perpendicular direction than the parallel one. The result is that the dense structures formed by turbulent compression in a magnetized cloud tend to be elongated along the magnetic field, and the field lines in those structures tend to be oriented in organized directions relative to the structure's long axis. This anisotropy is part of why molecular clouds are not simply round, diffuse objects. They are built of filaments, sheets, and elongated clumps, structures whose shapes reflect the geometry of the magnetic fields that helped compress them. One way to begin to feel the scale of what the magnetic field is doing is to consider how slowly the cloud changes despite all of this activity. A giant molecular cloud is estimated to live on the order of 10 to 30 million years before its constituent gas is either converted to stars or dispersed by the energy input from those stars. Ultraviolet radiation, stellar winds, supernovae that eventually tear the cloud apart from the inside. 10 million years is a long time in the context of a human civilization, but in the context of the galaxy, it is a brief interval. A cloud forms, slowly makes a small fraction of its mass into stars, and dissolves, all in the time it takes the solar system to travel less than a tenth of the way around the Milky Way. And yet, within that 10 million years, the turbulence must be sustained. The magnetic fields must thread the collapsing cores. The ambipolar diffusion must bring neutral mass inward against the field. All of these processes running concurrently on timescales ranging from tens of thousands of years to tens of millions of years, all nested within each other, all contributing to the same slow and selective conversion of cold gas into light. The fact that only 1 to 3% of the cloud's mass becomes stars per freefall time is not a failure of gravity. Gravity is present everywhere in the cloud, pulling everything toward everything else with patient inevitability. The low efficiency is a consequence of resistance, the combined effect of turbulent pressure, magnetic support, and the long time scale of ambipolar diffusion working together to ensure that only the densest, most magnetically supercritical regions ever reach the threshold of collapse. The cloud holds most of itself in suspension, neither collapsing nor dispersing, maintaining the balance through mechanisms that are slow enough to seem like stillness. This is worth sitting with for a moment. In a volume of space 200 light-years across, containing gas equivalent to 1,000,000 times the mass of the Sun, the dominant physical outcome over tens of millions of years is most of it remains gas. The turbulence churns but does not concentrate. The magnetic field threads and supports. The gravity pulls and is resisted. The cloud drifts through its spiral arm, slowly losing mass at the margins where radiation and stellar winds eroded, slowly converting a fraction of its interior into stars, and slowly, eventually, falling apart. Not because anything dramatic happens, but because the cumulative energy input from all the stars it has made finally exceeds the binding energy of the cloud itself, and the remaining gas is pushed out into the surrounding interstellar medium, where it mixes with the diffuse gas of the galaxy and begins, over tens of millions more years, to cool and collect and perhaps become another cloud. The magnetic field travels with the gas as it disperses. The field lines that once threaded a star-forming core, that were dragged inward and pinched into an hourglass shape by the collapse, that eventually were mostly excluded from the protostar itself, as the ionized inner disk decoupled the infalling gas from the field. Those same field lines relax back into the surrounding medium as the cloud dissolves. The flux that ambipolar diffusion left behind in the envelope of the core is not destroyed. It spreads back out into the interstellar medium, slightly restructured by its time inside the cloud, and rejoins the larger magnetic field of the galaxy from which it originally came. Nothing is lost. The field remembers, in a loose physical sense, every cloud it has ever threaded. The turbulence that fills the interior of a molecular cloud is not chaotic in the colloquial sense, not random, not without structure. It is supersonic and highly organized across a wide range of scales, with velocity correlations extending from the largest eddies, several tens of light years across, down to the smallest resolved structures, and probably continuing below the resolution of any current instrument. The power spectrum of this turbulence follows a well-defined mathematical relationship across scales, similar in form to the turbulence in atmospheric flows and ocean currents, but operating at temperatures and densities and speeds that have no terrestrial analog. A wind that moves at 3 kilometers per second through gas at 10 Kelvin, encountering field lines that snap back at 2 kilometers per second, compressing filaments that will one day collapse into suns. This is what the interior of a molecular cloud is, all the time, everywhere, unseen. The compression events that turbulence produces are brief by astronomical standards. A shock front sweeps through a region, compresses the gas to 10 or 100 times its ambient density, and then the eddy that drove the shock dissipates, and the pressure differential relaxes, and the compressed gas either collapses under gravity if it is massive enough, or re-expands if it is not. The whole cycle, for a given piece of the cloud, might take 1 to a few million years. In the cloud as a whole, this cycle is happening simultaneously in thousands of locations at every moment of the cloud's existence, a vast, cold, dark, for in silent turbulent medium, constantly creating and destroying the conditions for stellar birth, with only a small fraction of the created conditions surviving long enough and accumulating enough mass to become something permanent. The permanence, when it comes, takes the form of a dense core that has accumulated enough mass to become magnetically supercritical in a region where ambipolar diffusion has moved sufficient neutral mass inward, where the turbulent support has declined to a level the gravity of the core can overcome. The core at that point begins its slow infall, too slow to watch, too gradual to feel, unfolding over hundreds of thousands of years in the same silence that has characterized every stage before it. But the cloud around it continues unchanged. The turbulence continues, the field lines thread. The ions and neutrals interact in their slow drift. In the large volume of the cloud beyond the collapsing core, the balance is maintained, and most of the gas remains exactly what it has always been: cold, dense, dark, suspended between the forces that shape it. The relationship between the turbulence and the magnetic field in a molecular cloud is not one of opposition, but of coupling. They exchange energy through the alpha waves that carry disturbances along field lines. They structure the same material in the same volume simultaneously, the turbulence producing overdensities in sheets and filaments, the field constraining which of those structures can collapse and which cannot. Where the field is strong relative to the local mass, turbulent compression creates structures that are stabilized against gravity by magnetic pressure, and they dissolve. Where the field is weaker, or where ambipolar diffusion has increased the local mass-to-flux ratio, turbulent compression creates structures that gravity can hold, and they persist. The interaction of these two forces, one chaotic and cascading, one ordered and threading the whole, produces the observed patchwork of star formation in a molecular cloud, dense cores forming in some filaments and not others, protostars appearing in clusters in some regions, while adjacent regions remain empty for millions of years. The Mach numbers of the turbulence in giant molecular clouds range from a few to several tens, depending on the size of the region being considered. Mach 5 means the gas is moving 5 times faster than the local speed of sound. At 10 Kelvin, the speed of sound is about 0.2 of a kilometer per second, and Mach 5 means the gas is moving at roughly 1 kilometer per second. Mach 20 means about 4 kilometers per second. These are not the speeds of gales or hurricanes, which are dramatic at human scales, but slow in astronomical terms. They are the speeds at which interstellar shocks propagate through cold gas, slow enough that they do not raise the temperature dramatically, a few tens of Kelvin behind a typical molecular cloud shock, but fast enough that they can compress gas by significant factors and drive the energy cascade from large to small scales that sustains the turbulent structure of the cloud. Everything in the cloud is in dialogue with the field. The ions feel it directly, their trajectories curving with every change in the local field direction, dragged by the Lorentz force that acts on any charged particle moving through a magnetic field. The neutral molecules feel it only indirectly through collisions with ions, through the pressure that waves in the magnetized medium exert on the gas as a whole. The dust grains are coupled to the gas through collisions, but their rotation is also influenced by the field, aligning them over time into the orientations that make them into tracers of the field geometry. The field does not act on any of these constituents in isolation. It acts on the whole medium at once, threading it and organizing it and slowing it, and the medium acts back on the field, dragging and tangling the lines wherever the turbulence is strong enough to overcome the field's resistance to bending. In the densest cores, the coupling between the gas and the field is greatest. The higher density means more collisions between ions and neutrals per unit time, which means the neutrals are more tightly dragged along by the field, and yet this is also the region where ambipolar diffusion is most consequential, because the higher density also means a shorter freefall time and a faster approach to the gene's instability. The two effects compete in the cores the way they do everywhere else in the cloud, but more urgently. The core that succeeds in becoming a star is the one where ambipolar diffusion has been operating long enough that the mass-to-flux ratio has grown above the critical threshold, and where the turbulent velocity dispersion has declined below the point where it can provide significant support. These conditions are met only in a small fraction of the cores that form throughout the cloud's lifetime. Most never make it. They form, persist for a while in quasi-static near equilibrium, and then either disperse as the turbulence drives the gas in new directions, or are disrupted by the outflows and radiation from nearby protostars that did succeed in collapsing. The image that comes to mind for the interior of a molecular cloud considered as a whole is of a vast dark body of cold gas in constant internal motion, not the motion of anything visible, not anything that glows or shimmers, but a slow supersonic churning that is revealed only in the Doppler shifts of radio spectral lines, in the statistics of turbulent velocity structure, measured across thousands of cloud positions, in the orientation of dust grains that have quietly aligned themselves with a field no eye can see. The turbulence fills the cloud the way silence fills a deep cave, not as an absence, but as a presence that has texture and structure if attended to with the right instruments. What the cloud holds back is the greater story. For every star that forms inside a giant molecular cloud over its lifetime, there are perhaps 30 or 100 times as much mass that does not become a star, that drifts and churns and waits and eventually disperses. The magnetic field, threading everything, slowing the drift of neutrals across its lines, propagating waves from one end of the cloud to the other at speeds measured in kilometers per second. The field is not preventing star formation, it is pacing it. It is the mechanism by which the universe ensures that the conversion of cold gas to stars happens slowly enough to be sustained over the billions of years the galaxy has been forming. Stars, slowly enough that the molecular clouds that will form 100 million years from now will still have gas to work with, slowly enough that the Milky Way has not already burned through its interstellar medium and gone dark. There is something in this that settles like the cold itself, not a drama, not a contest, just the long, patient physics of a cloud holding most of itself in suspension, threaded by a field that carries energy without consuming it, turbulent in a way that simultaneously creates and protects. The field lines run on through the gas in their quiet geometry, bending in the dense cores, organizing the dust grains into the alignments that will tell future observers which way the force was pointing, carrying alphen waves from one end of the cloud to the other at the speed of something between a slow breeze and a fast wind. By the standards of the interstellar medium, the neutrals drift inward, molecule by molecule, across the lines the ions are locked to. The turbulence churns and cascades and compresses and dissolves its overdensities, and a small fraction of them survive. In the vast cold volume between these events, nothing changes on any human timescale. The gas drifts, the field threads, the cloud holds most of itself in darkness and cold, patient and unheld by anything but its own internal balance, drifting through the spiral arm of the galaxy on a journey measured in tens of millions of years, making stars slowly at its edges and in its densest filaments, holding the rest in the quiet suspension of all the forces that resist. And slow and wait, deep inside a molecular cloud where no light has ever reached, a single dust grain holds still in the dark. It is not large, smaller than most bacteria that have ever lived, smaller than the width of a human hair divided into 1,000 parts. It drifts in a space so cold that cold itself feels like an inadequate word for it. The temperature around it sits at 10 degrees above absolute zero. Not cold, the way a winter morning is cold, or cold the way a mountaintop is cold, cold the way the near absence of all motion is cold. Cold is the near floor of what the universe permits, and yet this grain is not empty. Around its silicate heart, layered molecule by molecule over millions of years, there is a crust of ice. Water first, then carbon dioxide, then carbon monoxide frozen at the outermost edge, where the temperature drops lowest. Each layer deposited so slowly that no single moment of its accumulation would be measurable. The grain has been here long enough for stars elsewhere in the galaxy to have been born and to have died, while it waited in the dark, untouched by any photon, unstruck by any other particle, suspended in a silence so complete that silence itself begins to seem too active a word. This is where the story of telescopes begins, not with the instruments, not with the engineers, or the mountain sites, or the algorithms that process the data. It begins here, in the dark interior of a molecular cloud, with the fact that almost nothing that happens in this place can be seen. Almost none of it reaches us. Almost all of it is, by every ordinary measure, invisible. The dust absorbs visible light the way deep water absorbs it. A beam of starlight, moving toward the center of a dense molecular cloud, does not pass through. It enters the outer envelope and begins to scatter. It is redirected, deflected, absorbed. The shorter wavelengths go first, the blue end of the spectrum stripped away by the first layers of dust, and what survives a little longer into the cloud is the longer, redder light, faint and shifted from its original color before it too is taken. Deep in the core, no visible light reaches at all. The dark nebulae that appear to ground-based observers as blank silences against a field of background stars, regions where the stars simply stop, where the sky becomes a solid black, are dense enough that thousands of magnitudes of starlight are swallowed before a single photon can pass through. Anything happening inside those dark regions is sealed away from ordinary observation as completely as if it were happening behind a wall of lead. This is the central observational fact of star formation. The places where stars are born are the places ordinary light cannot enter. The processes that matter most, the slow compression of gas, the assembly of molecules on grain surfaces, the first stirring of gravitational collapse, the emergence of the protostar at the center of its collapsing envelope. All of it happens behind a curtain of dust that visible light astronomy cannot pull aside. Learning to see through that curtain took most of the 20th century. It required building instruments sensitive to wavelengths of light, far longer and far shorter than anything the human eye responds to. It required placing observatories above the atmosphere or on the highest and driest plateaus on Earth, where the air holds almost no water vapor to absorb the incoming signals. It required understanding that the same grain of dust that blocks visible light glows faintly at longer wavelengths